Hello, students. Today, we're going to talk about one of the most important foundations in chemistry, how we measure and describe the world around us. In this short lesson, we'll cover a bunch of things: units, the SI system, measurements, accuracy and precision, significant digits, and scientific notation. Phew. These skills might all sound like details, but trust me, they're the language of science, and they'll help you solve all the problems we do correctly and clearly. In chemistry, we do a lot of experiments. We talk about combining an amount of substance A with some amount of substance B, but what amount? If I tell you to put in 12, you would automatically ask me 12 what? 12 teaspoons? 12 pounds? 12 tons? A unit is simply a standard way to express a measurement, and in science, we have to have them. Without units, numbers are absolutely meaningless. To avoid confusion between one person's foot and another person's maybe cubit, scientists now use a system called the International System of Units, or SI for short. We also frequently call this the metric system. SI units are like the universal language of science. No matter where you are in the world, scientists agree on these basic units. But do we use them in the US? Believe it or not, I remember when I was a kid in 1975 when there was a federal law passed declaring the SI system to be the preferred system for trade and commerce. This was a big deal. My brothers were trying to convince my mom that she would be so much happier on the metric system when all of her recipes had been converted, and that she should buy them a computer where she could store all of her new recipes. But you may have noticed that preferred in the law isn't the same thing as must, and we still use the English system very commonly in the United States. So, despite the difficulty of getting someone to transition, the SI system is internationally accepted, it's scientifically clearer for communications, and it's much easier when it comes to doing that. We will use the SI units in this chemistry class. The base SI units we use in chemistry are meter for length, kilogram for mass, second for time, Kelvin for temperature, and the mole for substance. We'll get into this a bunch later in class. But did you notice that one was missing that we use all the time in chemistry? How about volume? If I pour liquid into a container and measure it, that's usually volume. Volume turns out to be a derived unit, meaning that you can build it from the other base units. So you can describe volume in cubic meters. That's 1 meter times 1 meter times 1 meter. But the most common units of volume that you've probably heard of are like cups, quarts, gallons. And the SI unit that we use for volume is called the liter. A liter is actually a tenth of a meter, or a decimeter cubed. It is really close to the volume of a quart. So this is a liter container, and this is, you might recognize, a quart jar. You can see they're just about the same. The liter is just a little bit bigger than a quart. It takes a little bit more than 1 quart to make a liter. Have you ever heard of a half gallon of soda? Strangely enough, we don't measure soda in gallons, even though we talk about quarts of things. We usually say, we're going to go buy a 2-liter bottle of soda, right? And you'll notice right here on this bottle, if I can get this up to the camera, hopefully you can see it somewhere here, you might notice that it says 2 liters. It also says 2.1 quarts. So you can tell a quart is a little smaller than a liter. So that's an interesting thing with our volumes, that we use totally different volumes in science than we really use every day in the US. By the way, when I said decimeter, did you wonder about the prefix deci? You're probably more familiar with things like kilo, milli, or even giga. These prefixes all indicate a magnitude bigger or smaller from any base unit. So the large prefixes like kilo, hecto, deca are all derived from Greek words, and the smaller prefixes like deci, which is 1/10, or centi, which is 1/100th, or milli, which is 1,000th, are all derived from Latin. And they just went one way with Greek and one way with Latin so that we could tell the difference between if we were doing thousandths or if we were doing thousands. Once you learn all of these prefixes, you can tell how to convert between SI units really easily. You just move your decimal place the right number of places one way or the other, and you can convert your units. So much easier than English. Now that we have some feeling for this units, we can use the units to measure something. When you measure something, all you're really doing is comparing your thing to some standard thing. For example, if I take this beaker and let's see, I'm going to say, I want to say how much is in this beaker. Well, this beaker holds 500 milliliters, and I need to compare the liquid to some lines on the beaker. Let's see if you can see that. So basically, I'm going to say, and you probably can't see it very straight, but I'm going to say I think it's just under there's a little line between 200 and 300, so maybe 245 milliliters. That's as accurate as I can get, right? I can compare this to some measurement on here, but I can't tell you that it's 245.638. I just can't tell with this beaker, right? So I have to go with the closest that I can come with the measurements that I have been given with my measuring tool. If I'm using something like a ruler, you might notice on my ruler, it's hard to see with the glare, sorry, but maybe I have millimeters on there, or maybe I'm doing inches and tenths of, we don't do tenths of inches actually, we do eighths and halves and super confusing things with inches too. But I can only go as accurate as my ruler is. So I might be able to measure like a half a millimeter on here because I can tell if it's between two lines, but that's as much as I can get. So when we talk about significant digits, it's a really important thing to learn because what we're saying is that all I can tell with my measurement is that significant digit. So you can't report numbers out to some huge number of length of numbers, digits, we call each number in a line is a digit, right? So you can't have more digits than are significant. The only significant thing I can measure is what my measurements are. So in this case, I said I thought it was about 245. So we're going to talk about tons of rules in this lesson about significant digits, but there's sort of just a basic rule of thumb is that whatever your measurements are plus one extra digit that is your sort of guessing is as many as you can have. So measuring this one, you'll notice that there was a line for 250. And beyond that, when I guessed 245, that third digit from 250, 250, the 2 and the 5 are significant. 245, I have three significant digits, and I was sort of guessing on that third one. So that's my rule of thumb. And then when you do the math, you can't come out with more significant digits at the end because you are indicating a level of accuracy that you don't actually know. The same thing, by the way, goes for scales if you're doing mass or weight or any other measuring instrument. By paying attention to these significant digits, we communicate both the value and the confidence we have in our measurement. One last note on numbers. Chemistry deals with numbers that are really big and really, really small. For example, a very important number in chemistry is Avogadro's number, which is 602.214076000000000000000 particles in a mole. This is 602 sextillion, 204 quintillion, 76 quadrillion. You might have noticed that's a little bit hard to say. So to manage these really big numbers, we will use scientific notation. That means you convert the number and you write or say it as one digit, then the decimal place, and then the rest of the significant digits after that. Then you add a times 10 to the power of whatever, however many powers you had to move the decimal place. It's important to understand powers in math when you're doing this, but you're just by simplifying this, I'm saying you're just multiplying by tens or you're dividing by tens to get your big number to something that you can write. So you could say that my measurement of 245 milliliters is really 2.45 times 10 to the second power. And Avogadro's number is 6.02214 times 10 to the 24th. Are you overwhelmed with numbers yet? Don't worry, you really will have time to let it sink in as you study these concepts this week. But there is one more thing you need to understand about measurements before you get started on your work, and that is the concept of accuracy and precision. In science, we use these terms to mean two different things that are both very interrelated and both very important. Accuracy is how close your measurement is to the true or accepted value of what it should be. Precision is how close your measurements are to each other, even if they're not correct. So, for example, if I measured length with, well, instead of a ruler, let's say I'm going to use my knuckle. That's about an inch, right? So I'm going to just say, Well, the accuracy is a little bit in question if I'm using my knuckle instead of, say, a ruler with an inch on it, right? But my precision is how carefully I use that knuckle to measure. Or let's use the beaker, it's a better example. So the accuracy might be how well these lines were painted on this container, but the precision is how I look at it. If I read it like by looking down once, I might get 300. If I read it like this, I might get 200. But if I look straight on, I get 250. So my precision is how well I use the tool. And if I do it different every time, I won't have precision. It'll be scattered all over. So another example of this might be think about if you're playing darts. If you're throwing darts and all of your darts are kind of around the center, but they're in a big group, they're scattered all over, then your accuracy is pretty okay. You're trying to get to the center of this dartboard, but your precision is off because they're scattered all over. Or maybe all of your darts are gathered together on one side, but they're really close together. Then your precision is good. You're doing it the same every time, but your accuracy is off. What we really want is both accuracy and precision. You need all of your darts to be going into the center of the dartboard, and you need them to be close together. So this is why it's important in science and in our measurements that we have to have both accuracy and precision in order to communicate with other scientists. Before we finish, let me recap. Units give meaning to the numbers that we use. SI is the standard system that all scientists use for their units. Measurements we make are limited by the tools we use and by how well we use those tools. Accuracy and precision are both very important in getting meaningful measurements. We need to use the right number of significant digits to communicate the certainty of our measurements to other people. And scientific notation helps us work with very large and very small numbers and still be able to write and communicate them clearly. These all may seem like small details, but together they form the foundation of communications in chemistry and science. Every calculation, every experiment, every result depends on clear, accurate measurement. So as we move forward, remember, numbers in science aren't just numbers. They tell a story about the physical world and how carefully we observe it.